We've covered most of the basics of basics now for chemical kinetics. What remains, in this most basic section at least, is to talk about a little bit more about how the simplest and most basic of simple reaction mechanisms work. We're going to talk about three different kinds of mechanisms. The first are sequential mechanisms. These are pipeline mechanisms where, starting from one reactant, we go through some series of intermediates. It only shows one intermediate here, but in general there's several, and finally ends up at some product, and every step along the way is irreversible. So that will teach us a whole lot of lessons. It's probably the most instructive of all the mechanisms we're going to look at, and we'll see what those are when we get a little bit further down. The second type of basic mechanism are the branched or parallel mechanisms. So here it is written out elementary reaction by elementary reaction, or here it is written out more in the sort of traditional diagram approach. But the idea of a sequential or a branched mechanism, is that you have a single reactant which can go to more than one kind of product with different rate constants for each case. And so how fast the reaction goes this way versus how fast it goes this way determines how much B you get or how much C you get before all the A runs out. So if K1 here is very fast and K2 is slow, then you get a lot of B, and vice versa if K2 is fast and K1 is slow. The third case is probably the second most important case, or maybe the most important case, depending on how you view it. That's a case where you have a reversible reaction. You have an A goes to B, but you also have a B goes to A. And so the importance of this case, and some very basic relationships come from this case, let me say. The importance of this case is that it allows both A and B to go to equilibrium. These other cases, I didn't point this out when I was saying something about them a minute ago, but all of them have nothing but irreversible reactions, right? The reaction arrows only go one way. They never go back. That means these systems can't go to equilibrium. The A goes completely away in the end. I goes completely away. Everything ends up as a P in the end. And there's no P ever going back the other way. Likewise, with this branched mechanism down here, A goes away, and it goes either to A, to B, or to C, but it never goes back. And therefore, there can be no equilibrium between the reactants and the products. But in this case down here, things do go backwards. A goes to B, B goes to A. And at the end of the reaction, if we wait an infinite amount of time, we don't end up with 0A or 0B necessarily. We end up with an equilibrium concentration of both. That also suggests, as we'll see, that there's some relationship between kinetics and equilibrium, and therefore thermodynamics. And in fact, we'll see that the rate constants are closely related to equilibrium constants. And that relationship between the equilibrium constants and rate constants is an extremely important one. Hard to overemphasize how important that is. So this is also a very important reaction mechanism. All right, let's just go through these then one by one, starting with the sequential reaction. So a sequential reaction, as it sounds, is just any series of reactants going to intermediates, however many there are, and finally ending up as some product. The overall reaction is just A goes to E, but there's some set of intermediates here, as many as we like, in between A and E, and understanding how the intermediate concentrations build up and then decay down. And since everything is irreversible, we know everything's going to end up at E in the end. But that means that and everything starts at A, of course, but that means that the intermediates concentrations rise and then fall, and understanding that is what we'll be looking at. And that and many of the implications of this mechanism. All right, so here's how things then look. You start with some A, you wait a little while, the A goes down, but now B is building up. You wait a little while after that, and B will start to become C, will start to go over to C. But what happens, I mean, in order to get to E, you have to go through every single intermediate. Start at A, end up at B, then go to C, then go to D, then go to whatever is next. If even just one step is blocked or is just slow, then you can stop the whole reaction. Things can't get any further than the slowest step, and the slowest step controls the overall rate at which you get to E. It's something called a rate-limiting step. We'll talk more about that down below. But in the present case, what it means is once you get to B here, if the next step is slow, then after that, things can go on to C and D and so on, but they go on more slowly, which means you get a big concentration buildup on B, and finally things end up going to E. But the stuff that comes before the rate-limiting step and the stuff that comes after the rate-limiting step doesn't affect the overall rate of reaction very much. The thing that controls the overall rate of reaction is the rate at which things go from B to everything else. And we'll talk about that in more detail and more formally in a little while. All right, that leads us to the actual math. And at least for this case, I'm going to go through the math carefully so that we can see how things actually work. And to do that, let me use this other page over here. So, first of all, the overall mechanism is A goes to I with rate constant K1, and then I goes to P with rate constant K2. We can write the rate equations for all the species, right? A and I and P, I an intermediate, that's important. And so let's write the rate equations. dA dt is equal to K1 minus K1 times A. It doesn't depend on anything else, so this is already a closed and complete equation. Then dI dt has two contributions, one from the first reaction, one from the second reaction, plus K1 times A minus K2 times I itself. That includes a species that isn't in the derivative over here, so we're going to have to do something about that. This is not an equation that we can solve as it stands at the moment. And then finally, dP dt depends only on the concentration of A. It's Ki, that is, K2 times I. These are the three equations that we have to solve. It's a system of differential equations now, and that's one of the things that differs from the examples we did up above. There's now more than one differential equation that we have to solve. And as the systems get more and more complicated, you get a bigger and bigger system of differential equations that you have to solve in every case. Eventually you have to do it on a computer. It becomes too much of a mess to do it on paper, or it becomes even just impossible to do on paper. Okay, now the equation for A we can solve right away. It's already closed, and it's just a first order decay. A, we already solved this equation, in fact, is equal to A0 e to the minus K1t. It's just an exponential decay. And the decay occurs not even knowing or taking any account or having any effect at all on the other reactions that come afterwards. A just goes away, and that's all that we know. And it goes away with all the properties of a first order reaction, so that's normal. Having solved that, though, we can now plug that into this equation, this second equation. We have that di dt is now equal to K1 times A0 e to the minus K1t minus K2 times I. And now, this is just a function of time. I is the only variable that we have to solve for. It's the only thing that appears. So we now have a closed equation. We can now solve this in principle. It takes a little bit of work to do that, though, so let's look at that. First of all, let's note the following. That if I take the time derivative of the following quantity, e to the K1t, e to the K2t, times I concentration, then that's equal to, just taking the derivative, K2 e to the K2t times I plus e to the K2t times di dt. And now if I multiply that by e to the minus K2t, so I multiply everything on both sides by e to the minus K2t, then this cancels with that, and I get that e to the minus K2t time derivative of e to the K2t times I is equal to K2 times I plus di dt. And if you look up at the differential equation that we have to solve, there's a minus sign here, but once we move that over to the other side, that's going to become a plus sign. This side is most of what we need to solve our differential equation. And so we can write that e to the minus K2t times the time derivative of e to the K2t times I is equal to K1 times A0 times e to the minus K1t. That's the differential equation we have to solve now, but that's now much easier. If I multiply through by e to the plus K2t, I get d dt of e to the K2t times I is equal to K1 times A0 e to the minus K1 minus K2 dt, times t, sorry. And now we have nothing but time stuff over here, and everything over here is just a time derivative. If I integrate both sides, I get the following. I get e to the K2t times I, that's the integral of this side, right, which is already a time integral, equals K1 times A0, the integral of e to the minus K1 minus K2t dt, and the integral on this, and plus a constant, which I don't think I need. Let's see, this is from 0 to t on this side, and yes, I need a constant on this side, I'm sorry. This should be the integral from t equals 0 up to t on this side as well. I need that in order to get the integration constants right. And so I get e to the K2 t times I minus I0, right? That's this evaluated at t equals 0, is equal to K1 times A0 times this integral, which is minus e to the minus K1 minus K2t over K1 minus K2, evaluated between 0 and t. What a mess. Let me rewrite that. All right, so redoing that, that becomes e to the K2t times I minus I0 equals K1 times A0 times. Now I'm going to plug in these limits at the same time as I'm doing this. Well, no, I won't. I'll just do it all out. E to the minus K1 minus K2t over K1 minus K2 evaluated between 0 and t. And that is equal to I was going to skip some steps, but let me not. That's e to the K2t times I minus I0 equals K1 times A0 times minus e to the minus K1 minus K2t over K1 minus K2 plus 1 over K1 minus K2. I'm running out of space here. I've got to write smaller. All right, doing the rest of the algebra, and I guess I'll stop there with the algebra, gives us at the end, going back over here, the following. Here's the final result after some more algebraic manipulations. I is equal to A0, a combination of rate constants, e to the minus k1t minus e to the minus k2t. And that's, well, not too bad, not too complicated. It gets worse later on. And we'll look at it in a little bit to see a little bit more what it means. But one comment I can make right away is that as we've been going through increasingly complicated cases, both the business of solving the differential equations over here and the business of actually writing down the final answers over here have been getting more and more complicated. And that trend's going to continue. You can see that at some point it becomes impractical to keep trying to solve things on paper, and that's when you get out the computer. All right, so we have one solution now. Well, we've got two solutions now. We've got A and we've got I. Now we can use the fact that we know that the total of A and I and P has to equal the amount of stuff that we started with, right? After things start changing, we don't gain any more material than we started with. So the total concentration of A has to equal however much there still is left in A, plus however much leaked over into I, plus however much got all the way to P. And so we have that relationship. That means that we can write that P is equal to the initial concentration of A minus minus I. We have both of these now. And if we plug in and do some algebra, then we get, finally, the third expression that we need for the concentration of P as a function of time. Notice it involves these same exponentials. It's a little bit more complicated still than even the expression for I. But we have it now. And now let's look at these expressions that we've derived and see what they mean. And I think for that purpose, I'm going to be able to do things entirely over on this side. So I'm going to close that window over there. Shrink this down a little bit just to make it a little easier. All right, so first of all, for the first expression, I already said this is just a simple exponential decay. We're familiar with that already. It has all the properties of a normal first-order exponential decay. There's a half-life and all that stuff. There's linear plots and everything if you want to go look at what was set up above. One comment that's worth making is that the reason the reason A goes away entirely independent of what I and P are, is that because the reaction that's destroying A is irreversible. And so all the A is going to go away eventually. And we won't ever get anything like a real equilibrium situation. I already said that, but let me just reinforce that here. Then for the second case, let's just look at this factor here. So this is the overall solution, everything here, but let's just look at this last part. If we set t equal to 0, it's always useful to look at some limits. Whenever you get a new formula, look at the extreme limits to see how things behave. So if we set t equal to 0 here, then that exponential right there is a 1. That exponential right there is also a 1. 1 minus 1 is 0, and so the intermediate concentration is 0 at time 0, as of course has to be the case, because if we start with A and then go to I and then go to P, and there's no I0 to start with and there's no P0 to start with, then there can't be any A. Then I has to be 0 at time 0, and that's what we're seeing in the formula. Also, if we let the time go to infinity, then this exponential becomes a 0, right? We get e to the minus infinity here, and that exponential also becomes a 0. We also get e to the minus infinity. We get two zeros, and that means the intermediate concentration also goes to 0 when time goes to infinity. And that means that in between there must be some kind of maximum. The intermediate concentration rises and then falls. It rises from 0 at the start and then falls back to 0 as time goes on, of course, the reason for that is that A is going to I, which is then going to P, and everything is draining eventually to P, which means both of these guys have to be going to 0 at long enough times. It is possible to find the location of that maximum point, to find what the value of the I concentration is at that maximum point, and that's kind of important because how much intermediate you eventually create is one of the most important things about this whole mechanism. So whether you make a lot of intermediate or just a very little is important to know. Here's the formula. I won't look at it in great detail, except to plug in a couple of test values. Let's pick a couple of cases. Let's suppose case number 1, that K1, the first of the two rate constants, is just 1, and the second rate constant is much faster. So this is now slower, and this is fast. What's going to happen in that case? Sorry, I have it backwards. K1 is the fast one. It's 10 times faster than K2. So this is the fast. Yeah, that's right. This is the fast one, and this is the slow one. And what's going to happen in that case is lots of A is going to get converted to I, but then the I is only going to convert slowly to P, and that means we're going to get a lot of I, a lot of intermediate building up. And that means this maximum value for I should be a pretty high value, and in fact it is. It's about 0.77 times A0 here. I actually left out the A0, so this has got an A0 in it too. And this is really I max over I0 over here too. So in that case, if we have a fast first step and a slow second step, intermediate builds up and reaches a high concentration. But if we have now let's suppose we take the other case. We take that K1 is only 1/10 of K2. So K2 is 10 and K1 is 1, let's say. That means we have a slow first step and a fast second step. What happens in that case, every time the A builds up fast, the A creates I fast, but every time an A gets created, sorry, I take that back. Lots of mistakes this time. The A's create the I's slowly in this case, but then every time an I is created, it's destroyed rapidly, and that means the I concentration never has a chance to build up. That's reflected in the formula here. It's e to the minus 1, or 10 to the minus 1 basically, or about 0.1 actually. And so the I concentration in that case is, the I maximum concentration in that case is low. And all of this is illustrates the idea of a rate limiting step that I talked about earlier, because in the case where the first step is fast and the second step is slow, this is the rate limiting step. And in the other case where this step is slow and the other one is fast, then this is the rate limiting step. And stuff builds up. Concentration always builds up on the species that's right before the rate limiting step, so it builds up on I. In this case, it builds up, or really goes away only slowly, and is probably more accurate, on A in this step, because the very first step is the rate limiting one in that case. All right, finally we can look at the concentration of P and how that's varying with time. If we set T equal to 0 in this case, that becomes a 1. That becomes a 1. We get K1 minus K2 on top here. We get K2 minus K1 on the bottom. That's a minus 1 overall for this whole term. It gets canceled by the plus 1 and we get 0 for the initial product concentration. That's exactly, of course, what we said and what has to be. Can't have any P at the beginning. Also, when T goes to infinity, if you play with the numbers, I won't go through them a little bit because they're a little bit more complicated in this case. But if you go through the numbers, if you set this equal to 0, for example, well, actually you can see it. Set that equal to 0 as T goes to infinity, this whole term goes to 0. and you just get P is equal to A0. So as time goes on, the concentration of P builds up until it finally, after a long enough period of time, it becomes equal to the initial concentration of A0, of course, because now everything has transferred itself all the way to the end of the mechanism to P. All right, here's a couple of plots. This was actually a homework problem that shows how this looks for 3 different cases, and I'll leave that to you to work on for the homeworks, and I think we'll stop there and pick this up again next time.